6.3 problems. This is basically a review from the top of page 1 of 6.3 lesson. If delta G is a negative number, the reaction wants to go forward, and therefore Q is less than K. You might need to hit pause and have a deep think about this, but these are both fractions, and if this fraction is less than that fraction, then one way to put it is you don't have enough numerator, which means you don't have enough products, which means the reaction has to go forward and create more products and grow this in value until such a point when it reaches K, and then it will be at equilibrium. If delta G is 0, then we are at equilibrium and Q is K. If delta G is positive, the reaction wants to go in reverse, and we know that Q is bigger than K. And again, these are fractions. If this fraction is bigger than that one way to put it is that you have too much numerator, too many products, and the reaction needs to go in reverse and get less products and make this number get smaller until such a point that it reaches that smaller number and you hit equilibrium. On table 2, we can actually make some predictions about the nature of the number of K if we know delta G standard. Now at standard state, Q equals 1. That's kind of the definition of the standard state. And if delta G standard is 0, then it's at equilibrium at the standard state. And we know that at equilibrium, K equals 1, and we just said Q equals 1, so these are all true. K is Q, which is 1 at equilibrium, which brings me to that middle line. If delta G standard is 0, then we're at equilibrium, and K equals 1 for the standard state only. For the standard state only, I need to really emphasize that. I am not saying that anything at equilibrium has a K of 1. And we know that because we've done many calculations where we assumed that K was not 1 because we were told it was stuff like 0.09 in 6.3 lesson, for instance. So K is not always 1. In the standard state, it is 1 because Q is 1. And if we're at equilibrium, then K is true. But we just said Q is 1. The current math on the K math is Q. You do it and you get 1. We know that at the standard state, Q equals 1, and we know that at equilibrium, K equals Q. Q equals K. So these are all three equal to each other at equilibrium. If delta G is less than 0, then the reaction wants to go forward, and therefore, in the standard state conditions, if this is equilibrium, then it must be wanting to go forward. We have more products than we do when K equals 1. Since we can consider this a fraction, the number we have to get to reach equilibrium has more products than when we had the fraction equal 1. At equilibrium, the fraction was equal to 1. Here, we need more products than this. The reaction needs to go forward from that point, forward. And we also know that because delta G is a negative number. Delta G standard is a negative number. Delta G standard is a positive number, then the reaction wants to go backward. And we know that K is smaller than 1. Again, this is true at equilibrium, and this is a fraction. If this needs to reach a number smaller than 1, then the products in the numerator need to reduce until such a point as the fraction reduces to hit this value. So the reaction needs to run backward and get the numerator smaller and the denominator bigger. It needs to reduce the products and increase the reactants to become a number smaller than 1, which was true at equilibrium. And again, we know that delta G standard being a number greater than 0, a positive number means the reaction wants to go in reverse. So this all works together. The great thing about reality is that it doesn't have plot holes. You can't find breaks in it. It all reinforces itself. So if it seems like I've been saying the same thing 5 times, I kind of have been. That's my point. You can look at it from a bunch of different viewpoints and you keep getting the same answers. So supposedly we go to a table of thermodynamic values, but let's just pretend. In reality, of course, they would have just given it off to the side. But what we're going to use is the delta H of formation, the delta S of formation of these chemicals. So we're going to take this times 2 minus this times 1 minus this times 3 and get the delta H standard. Remember that a delta H formation of an elemental form is a 0. So same thing on the second line, we're going to take the delta S formation numbers given, we're going to multiply by 2 and then subtract out 1 of these and 3 of those and get delta S standard. Now to calculate delta G standard, we'll use the Gibbs free energy equation, and if we put in the standard values, we get out the standard value. Don't forget to use the Kelvin temperature, and don't forget to make this kilojoules by pushing the decimal left 3 spots. To find K, you're going to have to put it into this version of the delta G and K formula, and you're going to have to remember how to generate this from the one given in the booklet. This is not the version. We now know delta G. R is given in the booklet. Make sure to get the one with joules. I know that's not here, but it is with joules. They skip the units in this example. And don't forget to use the Kelvin temperature. Oh yes, also, you're going to want to convert probably this to joules because this one has joules and this one is in kilojoules. Here, kilojoules. So you cannot just put in kilojoules and then the constant because the units don't match and your answer for your exponent will be off by a factor of 1,000. Also, don't forget to be very careful about the signs. There is a negative in the formula. And it's very tempting to say, oh, negative, put it in, check the formula and say negative, yep, I got the negative. No, you need the negative from the value and also the negative from the formula. You're going to get a positive in this case, a positive exponent. And then we take the inverse natural log to get the actual value of KEQ. C is pretty much a repeat. If we can assume that delta H standard and delta S standard don't change when the temperature changes, and I don't know why they wouldn't, but it looks like we're going to pretend that they don't. We're going to use them again. What we're just going to change then to find delta G standard is the Kelvin temperature, and we get a value for delta G standard. Now, the reason that we really need to do that if we're going to get KEQ is that we don't know delta G standard at this temperature. Also, I know this says KP, but none of this was emphasizing the pressures. So why don't we just go call that KEQ? And by the way, if you're listening to this and you're wondering why we're not converting between KC and KP, because there is a formula and it is in a lot of books, it's even somewhere in this workbook, it's because I double checked the booklet from the real test and that formula is not provided, which means they can't ask for converting between KP and KC. Now that we have delta G standard, we can put it in here. Make sure again to get the R that has the joules in it, put your temperature in Kelvin, and remember that this is in joules and that's in kilojoules. So let's multiply that one by 1,000 to get joules. Don't forget your negative sign, and then take inverse natural log to get your final value for KEQ. Again, apparently there's some table of thermodynamic values, and what they must have done here, although I know it's not super obvious, is gone and used the delta G of formation of these chemicals. So again, we'll have one of these and one of those, minus one of these and one of those, because for every 1 mole of runs of the reaction, we need one of these and one of these and one of these and one of these. So we'll multiply by 1 and subtract out 1 and 1. However, the delta G formation of an elemental state is 0. And we get a number less than 0, which means it is thermodynamically favorable. It wants to run in the forward direction at the standard state. On B, we want to find KEQ. So again, we're going to take the delta G standard, which we found back here. We're going to put it in the exponent there. Don't forget the negative sign that you generated. And then don't forget the negative sign in the formula. Obviously, that makes it positive. Divided by that gives you that inverse natural log. It gives you that value. This formula is not on the test. I double checked. However, I'll explain it for the purposes of the mental exercise and people who are going to end up in a chem class in college. So if we know this formula, and you might remember from 6.3 lesson that this is the more fundamental form of the formula, where we have Q and delta G of reaction under the current circumstances. This is not the standard form. This is the standard form one. Then we can find Q because we know the partial pressures, and Q sub P, so to speak, will be products over reactants to the power of the number in front. Well, we get 1E negative 10, and this is E negative 12, but we subtract the bottom exponent, so it's 10 minus negative 12 is positive 2. 1 over 2 is a half, times 10 to the 2 is 50. That goes in here. Natural log of that, times that, times that. Turn this joules into kilojoules by pushing the decimal point 3 spots left there, and then add in that, and we get a value for delta G reaction in the current circumstances. That's why we had to use Q and not K. It's not at equilibrium, it's the current circumstances. So we have to use Q instead of K. On the backside, we have an old real chemistry problem. I will point out that this is before the 2014 revision, and I can tell at least in one way. I don't recall the current version of the test asking you for the empirical formula of a covalently bonded compound. That's not very useful. I don't quite know why they ever bothered asking that. Anyway, there you have it. And read through all of this. Now, we want delta H in kilojoules per mole. So this is a very complicated way. I would rather do it like this. I'm going to take my grams of glucose, use the grams per mole, get the moles. It's 1 mole of glucose for 1 mole of reaction. Because remember, what I really need is per mole of reactions. The delta H standard is going to be per mole of times the reaction is run, per mole of reactions it is run. The delta H standard is going to be the kilojoules for every mole of times the reaction is run. Now that happens to correspond with the moles of molecules that are used, because if you use 1 molecule, you get 1 reaction run. That's this conversion here, and I get 0.0139 moles of reactions that are run. I put that under the kilojoules. Remember, it's a negative because we know it was released, and we get a kilojoule per mole of reactions, invisible there, value for delta H standard. Then they give us the fermentation reaction, a delta H standard, temperature, and a K. So what's delta G standard? Well, here's the sort of standard version of this equation. Push your decimal point 3 spots left on your R value to get it into kilojoules, put in your Kelvin temperature, and put in your K value, and multiply it all together. Don't forget the minus sign, and we get delta G standard. Here we're going to take the delta G standard, put it back into Gibbs free energy, because what we're looking for is delta S standard. We know delta H standard from back up top. We know the temperature, and we can solve for delta S standard there. On triple I, this does get confusing, and what I'm going to leave it at is, because delta H standard is a negative value, the heat lives on the right side of the equation. The heat is coming out. Therefore, by Le Chatelier's principle, if you put heat into the system, it drives it back left, and going back left means K is getting smaller. I realize there seems to be a contradiction with the idea of putting temperature, a higher temperature, into Gibbs free energy equation. I've actually been asking somebody about that, and I'm just going to leave it at the idea of saying that the Chatelier's principle idea is the predominant factor here, and that's all you're going to need for the test. The idea of the seeming contradiction between that idea and the Gibbs free energy isn't going to come up, so I'm going to skip it. D is pretty darn complicated, and as I recall, they stopped asking questions in this manner on the current version of the test. I think they were getting a lot of wrong answers just because people didn't even understand what they wanted. What we're going to do, though, and I don't think the instructions are all that clear, is generate this reaction from the reaction in part A and in part C. And we're going to do Hess's law on them. We're going to flip and multiply as needed such that they cancel out to generate this, which is that. So if we take the one from part C and flip it and multiply it by a half, and then take the one from part A and multiply it by a half, they actually cancel out. Take a moment and look through to this, which means we have to multiply this delta H standard value that we had for this one by a negative half. Remember, we flipped it, so that's why the negative sign. And we have to multiply this one by a half, and then we add up these values and get the new delta H standard for this reaction. For the top of this paper, for the moment, ignore all my penciled in notations, okay? We'll get back to that. For part A, we're asked about reaction X. What would be Kp? Well, it would be products over reactants, the power of the number in front, using the gases and very much not the solid. That is the way to lose that entire point, is to throw the solid into a K expression. It doesn't have a molarity, it doesn't have a pressure. You're also going to need not to put the brackets because that indicates molarity, and they specifically asked for K based on pressure. You're going to need the pressure of. For reaction B, let's remember that we're talking about delta H standard, delta S standard, delta G standard. So we're already talking about 25 degrees Celsius or 298 K. So for reaction X, delta H is a positive number, which means the heat sits on the left. Giving it more heat, then we'll drive it to the right. More right is a greater K value. And so Kp increases. For reaction Y, is K greater than 1, less 1, or equal to 1? If it was 1, then it would be at equilibrium. But we know that delta G is not 0, which would also be true at equilibrium. Delta G is a positive, which means this thing wants to run reverse at standard conditions. So K is less than 1 because at equilibrium standard conditions, K is 1. So if it wants to run left at standard conditions, K must be less than 1. It must be wanting to create more reactants, which in that K math means that the denominator is bigger than the numerator. For reaction Y, the delta H value is a positive, which means the heat sits on the left. You have to keep pumping energy into this. The heat is going into the system overall, which means there's more energy on the right side than there is on the left side, inside the chemicals themselves, in the bonds. So the energy of the right side bonds is greater than the energy of the left side bonds. For E, that's a pretty good explanation. The only way to predict a reaction rate, if all you have is the overall reaction, is to do the reaction 100 times and get good data. It cannot be predicted from the overall reaction. It cannot be predicted from delta H or S or G or anything. We just have to do it. We just know whether it wants to go forward or reverse, or is at equilibrium. We don't know the actual rate from anything on this page. For F, we can determine the sign of delta S standard just from looking at the reaction. We have 2 molecules of gas becoming 1 molecule of gas, which means that the overall delta S standard is a negative sign. Remember that the negatives and positives on delta S kind of indicate the opposite of delta H. This is thermodynamically unfavorable, and that's a negative sign on delta S. Favorable is a positive sign on delta S. So for F, we know just from glancing at it through there that the sign is a negative. Then the second part of F, we're going to have to do something kind of complicated, which they don't really indicate, and they stopped asking for this kind of mental leap from what I can remember. Notice this is from 2009, before the rewrite of the test. We're going to have to use Hess's law to get delta H standard for reaction Z. If we flip this one and flip this one, they cancel out and make this one. Hit pause and work through that, but they do. Which is why I put a negative sign on all these. That's why. If you're going to run these backwards, then all these signs change. And then if that's negative and that's negative, then they add up, and this is the value for delta H. Don't forget the units in your real answer, of course. Of course, they're telling you the units anyway, aren't they? Giant clue. For the third part of F, if you give it just CO, you're taking two gas molecules and generating only one, which means the pressure in the vessel has got to go down as this goes forward